Hello everybody, this is Parinas and Gayatri and I will give you this presentation which is about unbalanced data. In the slides we will understand that what is unbalanced data, how we can deal with them, what methodologies we used and what results we obtained. So, what is unbalanced data? Data is said to be imbalanced when instances of one class outnumber the others by a large proportion. Learning classifiers from imbalanced data is a very important topic. Sometimes in machine learning classification, the number of elements in each class change a lot, so can lead to have a wrong prediction. So we might have a class with a number of elements 3 or 4 times more than the number of elements in other classes. So in this case, the classes with few elements tend to be poorly predicted because as they are underrepresented and these classes are usually more important. And so we can see that traditional classifiers are not really suitable to deal with imbalanced tasks because they tend to classify all the data in the majority class, which is usually less important. Now the question is that how we can deal with unbalanced data. In our project, we changed the resampling techniques and we used a smooth undersampling and oversampling. A smooth is an oversampling method which it creates synthetic samples of the majority class. So it makes our minority class equal to majority class. Undersampling downsizes the majority class by removing observation till our dataset gets balanced. It can be a good choice when we have a large number of datasets, but the drawback of this method is that we might lose potential information. And for oversampling, it adds more copies of the minority class. So it do multiplication of existing minority class. It can be useful. It can it can be a good choice when we don't have a big number of data. But the drawback in this method is that it's highly prone to overfitting. So for our project, we choose a phishing dataset which 1,353 different websites from different sources were collected. Our labels are fishy, suspicious, and legitimate, and these labels are replaced by numeric values of -1, 0, and 1. As we can see here, 702 is our fishy data, 548 is legitimate, and just only 103 of them are suspicious. So we can see that we are dealing with imbalanced data. And here we can see the attributes of our data. This table is showing us the correlation between these attributes, and if we want to look in detail, we can see, for example, web traffic has not much correlation with others, and if web traffic values change, the other attributes wouldn't change much. So in next slides, Gayatri will explain you about the methodologies we used and the results we obtained.
In our experiments, we have used the algorithms logistic regression and random forest on our dataset. We have also trained the TADA model on our dataset. We have used 4 modes of data: imbalanced data, that is the original data, upsample data, downsample data, and dataset created with smooth. The metrics we use to measure the performance are accuracy, Matthews correlation coefficient, precision, recall, F1 score, and balanced accuracy for TADA. We have split the dataset into train set and test set 10 different times using different random states. Here are the performance metrics we obtained from all our experiments. We can see that the upsample data in random forest has given us the highest metrics, whereas the data with downsample data gave us the lowest performance. Here is the consolidated metric evaluation for all three models, each performed on all four modes of data. The values are averaged from all 10 runs in each case. From the table, we observe that the random forest model with upsample data gave us better accuracy and also in all the other three modes. The lowest performance was shown by downsample data using TADA. Here are the results obtained while using the logistic regression model. We can see that the imbalanced dataset has performed better than the downsample for all the metrics. Here are the box plots showing the accuracy measure, the MCC measure, precision measure, recall, and F1 score for all 10 runs. While using random forest, we observed that the highest metrics were found using the upsample data, while the lowest was found using the downsample data. Here are the box plots for the random forest measures. Here are the results after performing data predictions on the dataset. Here we find the imbalanced dataset giving better metrics compared to all other modes, downsampling being the least. However, the precision for the imbalanced dataset is the lowest compared to other modes. Precision of TADA model on smooth data is high. Here are the box plots for the TADA model. While dealing with imbalanced datasets, accuracy is not a reliable metric. We can easily achieve a higher accuracy by ignoring the underrepresented class. To avoid this problem, we replace accuracy with balanced accuracy. Here are the averages of balanced accuracy scores with all the 10 runs for each mode of data using TADA predictions. We also find the individual runs with the highest marked in orange and the lowest with green. From our experiments using various models on original and preprocessed data, we observe the following. Upsample dataset performs better than the downsampled, smooth or imbalanced dataset. Tree-based models gives us better results, which in our case was random forest. Balanced accuracy is more reliable than accuracy. Resampling on small data leads to loss of vital data points. This is the reason why the downsample data gave us bad performance metrics. After analyzing our previous results, we propose few more ideas which might be of interest to deal with the imbalanced dataset issue. We can try and combine two or more approaches to see if we can obtain better results. We can introduce cost-sensitive methods by penalizing the model higher for incorrect predictions of underrepresented classes and by penalizing the model lower for incorrect predictions of overrepresented classes. We can also try various resampling techniques with different methods like with replacement or without replacement. We can try different tree-based algorithms with different hyperparameter tuning. We can also try feature selection to obtain better results. Thank you.